am Aswani, Assistant Professor, Department of CSE AIML at MLR Institute of Technology. Welcome back to another session of Artificial Intelligence. In this today's session, we are going to learn about recurrent networks. Let's see the overview of this session. Introduction about the RNN, architecture of RNN, half-field networks, one of the RNN networks, and characteristics of a half-field network. And we will see one of the example for a half-field networks, and we are going to see the Boltzmann networks also. Let's see the introduction part. So we have already seen the feed forward networks. Then now we came back to the recurrent networks. Then what is the difference between feed forward and recurrent networks? Why we use the recurrent networks? Already we are having feed forward network. So for example, if we want to know the stock market details or weather forecasting, stock forecasting or weather forecasting, we can't use this feed forward network. Why we can't use the feed forward network? And what is the use of feed forward networks? By using feed forward networks, we can recognize the images, and also we can use this as the writing analysis and email filtering. All those things we will use the feed forward network. Whenever there are some situations that says like if you want to measure weather, what is the weather tomorrow and what is the price of some particular stock or what is the time series, in that cases the feed forward network is not useful. Why it is not useful? Because it doesn't contain any memory. It will work on current data and that is fixed. Okay, let's see the feed forward network structure. The structure is acyclic. There is no past input data. There is no past history available to this feed forward network. Whatever current data is available, that is fixed one. And the flow of data is from input to output, and there is no cyclic values from that output data is fed back to the input. In the multi-layer feed-forward network also, it contains output node to hidden node to input node. It is not like that output node to directly input node. There is no such type of network in the feed-forward network. So here it is acyclic and data flows from input to output nodes. Next, how it will be trained. The training process is once trained and the state is fixed. Whatever data we will fit, the new data, then it will goes to the training and it will give the answer that will be fixed. Next, memory. No memory of past inputs. Whatever current data is there, it will work on the only current data. It won't remember the previous data. Next, use cases suitable for tasks where the current input alone determines the output. Image recognition. Okay, in such cases we will use this feed forward networks. Next, let's see the recurrent neural networks. The recurrent neural networks structure is cyclic. So the output is fed back to the input, allows feedback from output to input nodes and connections between any nodes. So n nodes are there means in the network, each and every node is connected to each other. Next, adaptability. Internal state can be modified with new inputs. Next, memory. It retains the memory of past inputs. So what is the yesterday's temperature? What is the day before yesterday's temperature? And today's temperature. It remembers the past data. There is a memory will be there in the hidden state and it will be stored that patterns. Depends on the current and previous data. It will estimate the tomorrow's temperature. The use cases are tasks where the output depends on the previous input, such as stock market prediction. The product's previous price will be predicted, will be used to predict the tomorrow's value, and weather forecasting also the similar way. Okay. How the learning process in recurrent neural networks. So feedback loop. Inputs are fed through the network with feedback from output to inputs. Look at the structure. So this one is the delay operator and this is the input nodes, one hidden node and output node. The output is fed back to the input nodes. That is what the feedback loop. The stability. After reaching some stability, after performing multiple times, it reaches some stable state. That state is called as equilibrium state. Once it reaches that state, if you are performing the further also, it won't change that output. At that state, it will stop the process. So the stability, the process repeats until output values stabilize, reaching equilibrium. Then it will stop that process. Next, recurrent networks can be trained by using backpropagation algorithm. In this method, at each step, the activation of output is compared with the desired activation and errors are propagated backward through the network. That is what in the previous sessions we have seen backpropagation. After computing the output, it will be compared with the desired output and computed output. Whatever difference is there, that difference is called as error. We need to reduce that error like a 0.01 means stable state. After this state, if you are not reducing the error, then we will stop that process. To do that, we will use the backpropagation algorithm, propagated backward through the network. Once training process is completed, the network becomes capable of performing a sequence of actions. So it uses the sequence of actions. The next one is half-field networks. These half-field networks are the one of the type of recurrent neural networks. The recurrent neural networks is the type of artificial neural networks. So here half-field networks invented by John Half-Field in the 1980s. The structure is consists of n connected neurons with symmetric weighted connections. So each link will have the weight. No neuron is connected to itself. There is no self mode. It will be connected to one neuron to another neuron. Neuron serves as the input, as the output, because it is one of the type of recurrent neural networks. So it will serve as the input as and also output. Next, how the operation will be performed. So here activation, binary value based on the sign of the weighted sum of inputs. So if it is a positive, then the neuron will be activated. If it is a negative, the neuron will be in the inactive mode. So update, neurons update asynchronously and independently, step by step. So at a time only one neuron will be updated. Next, there is a threshold will be there. Based upon that threshold only, whether the neuron will be activated or deactivated, we can observe that using this threshold value. Determines if neuron fires, activates connected neurons with positive weights. Next, processing. Input is applied simultaneously to all neurons continuing until a stable state is reached. Equilibrium state will be reached. Next, what are the characteristics? Recurrent networks. Output values are fed back into the network. What is the stable state? When it reaches the equilibrium state. Represent the network's output when all units remain unchanged. If you are performing multiple times, the output remains constant. Then that state is called as a stable state. Then functionality. Content addressable memory, which is used to store the patterns and retrieve the closest match. For example, if you can recognize your friend with the hat, with the glasses, even her face will changes also. It recall that patterns with the closest patterns, and we will remember our friends. We will recognize our friends. In the same way, the content addressable memory stores patterns and retrieves the closest match to a new input. Next, convergence, guaranteed to reach the stable state. Definitely it will reach the equilibrium state. Let's see the structure of half-field network. So here the nodes in half-field networks are binary threshold units that takes two different values for their states. 1, -1. There are two values will be taken. Each of these units may be either active or inactive. Active means 1, inactive means 0. The activation status of a neuron depends on the threshold and is given by its respective activation function. The activation function of ith neuron is if the threshold value is greater than the weighted sum, then it is 1, otherwise it is 0. First we will perform weighted sum up, and there is a threshold value. If that weighted sum value is greater than the specific threshold value, then that neuron is active, otherwise that will be inactive. Where Wij denotes the weight of the connection between unit I and unit j, Sj denotes the state of jth unit, and theta denotes the threshold of ith unit. The state of unit is either 1 or 0, representing active or inactive status to respectively to that node. So it should be noted that there are 3 parameters which we need to remember. No unit has any connection with itself. That is what in the first we have seen. Wii equal to 0 for all I. All connections between 2 units are symmetric and may possess positive or negative weights, and each unit is also either active or inactive. The neuron either in active mode or inactive mode only. Let's see, a positive weighted connection indicates that both units can active like this, or one is in active and another one is in inactive mode. The black is in active mode and the light circle is inactive mode. We have represented the active unit by a black circle and an inactive unit by white circle in this. So, positive weighted connection will be look like this: current state and new state. Next, the next negative weighted connection is in which an active unit can deactivate other unit if it is active. The negative means if that unit is active but it has a negative, then it will be deactivated. Look at this one, current state -2, the negative value. The next one, it will deactive. Otherwise, there are 2 possibilities in this situation, because in the 2 units are active state, but here the value is -2. Either it is the possibility solution, it can deactivate other one, or this one can deactivate the other unit. Let's see the activation algorithm. So choose a unit randomly and call it as ith unit. For ith unit, compute activation value as given below using sigma Wij into Sj for all j, where Sj is the state of jth unit, that means 1 for active unit, 0 for inactive unit, and Wij is the weight from ith node to jth node. If sum is greater than theta I for ith unit, then the selected unit becomes activated, otherwise it gets deactivated in case it is already active. Until the network reaches the stable state, this process will be repeated. So randomly take one value and compute the sum based upon this formula. Sigma Wij into Sjs is the state, either 1 or 0. If the unit is active, then we will take as a 1. If the unit is deactivated, then we will take as the 0 value. After that, perform sum is greater than theta specified threshold or not. If it is greater than, then that node will be activated, otherwise it will be in deactivate mode. The following algorithm represent the simplistic form of general algorithm. Here we compute the sum only active nodes connected to the selected unit. For example, here it is this one is the selected unit. This one is the activated unit, and this one is the inactivated unit, but here this one is a selected unit. So whatever connections are there, first we will check that connections. Here this one is active, so we will compute the sum to only the active units. That is what here the algorithm says. We compute the sum for only active units connected to the selected unit, because sigma Qij into Sj equal to 0 for inactive units, and so there is no need to compute such weighted sum inactive units connected to the selected unit. If you compute the sum also, this one will be 0. That's why it is the waste of time. So we will compute the sum to only active nodes which is selected and that is connected to the active nodes. That is what the algorithm says. The units of a given half-wheel network are activated using the algorithm. till the network status becomes stable. This process is known as parallel relaxation. So next one is application of activation algorithm. So this one is the current state. Okay, so these nodes are inactive nodes and these nodes are active nodes. So first selected unit for current state. For this state, first selected node is this one. So the new state is here. We will calculate the sum is only to the active nodes, that is 3 minus 2, which is connected with this selected node. This one is connected, this one is connected. So 3 minus 2, what is the value? 1. 1 is greater than 0. So activated. This one is also activated. So the selected state, whether it is active or not, we will find out the value, compute the value, and we will activate that unit. Okay, so the next one is here, this node is selected for this current state, this one is activated. We will find out the sum only to the activated nodes. Here only one node is activated. This here minus 2 is the value. Minus 2 is less than 0. So this one is deactivated. So the selected node will be deactivated. That is what half-wheel networks. So when the stable half-wheel networks, let's see one example. A half-wheel network is said to be stable if there is no change in the network. Let us consider one example of a network of 3 units, 1, 2, 3, fixed weights, 1 minus 2, 1, W1, 2 is 1, 1, 3 is minus 2, 2, 3 is 1. Initially, all units are inactive and represented by vector 0, 0, because there is no shade in black units. So the values are 0, 0. Next, the stable positions of networks. We can see that there are 2 more stable states of the half-wheel network in addition on the below diagram. Okay, using activation algorithm. Thus, now we observe that any input pattern given to the network will converge one of these states. So, if you observe the previous one, there are 2 positive values, 1 negative value. With this, we can draw like this. 1 and 2 active and 3 is deactive and 2, 3 is active and 1 is deactive. Let's see. So, 2, 3 is active, 1 is deactive and 1 and 2 is active, 3 is deactive. So, for whenever we choose like this, the random values, then the x values are 0, 1, 1. Because the first unit is deactivated, so we have taken as 0. The remaining is active, so it is 1, 1. In the same way, x is 1, 1, 0 and here 0, 0, 0 because no unit is activated. So it is clear that once weights have been correctly determined, we can generate a stable state which constitute the content addressable memory system. So how the weight computation? Let's see the method. Training example need to be provided in order to determine the weights of a given half-wheel network. This is the formula. Sigma xi into xi transpose. The method. Let's see here. x1, x2, x3. The 3 vectors. The formula is here. x1 into x1 transpose plus x2 into x2 transpose plus x3 into x3 transpose. And identical matrix with the 3. Why 3? Because we are having 3 units. So the same values, take that values and transpose values, and whenever we perform all this operation, we will get these values. And if you observe, all the diagonal values are 0, so we can say it is as symmetric. From the matrix above, we observe the diagonal elements of matrix W is 0. The matrix is symmetric. Thus, the network generated using these weights and input vectors are stable except x2, which stabilizes to x1. Finally, the obtained weight and stable states x1 and x3 we can stabilize by new pattern, and one of those given in the next diagram. So we can draw like this: 1, 3, 1, 2, 3, 4. The half-wheel network look like this: W1, 2 is minus 1, 1, 3 is minus 3. Based upon these values, we can draw like this: x1 values and x3 values. So, 2 nodes are 1 and 4 are active and middle values are inactive. In the same way, 1 and 4 are inactive, the middle 2, 4, 2, 3 are active. Okay. The next one is Boltzmann machines. So here, proposed by Hinton Sijnowski in 1986 as a derivative of half-field networks. So here the difference is units update their binary states using stochastic rule. So in the half-field network, normally we will use the deterministic values whether the state is stable or not. But in this Boltzmann machines, we will use the probabilistic values, stochastic rule rather than deterministic one. The probability of active state is P equal to 1 by 1 plus delta E divided by T. When delta E is positive value, then the less active, and negative value more likely to be active. So delta E is sum of active input connections to the unit. T is the temperature of the network. So what is how the behavior of the temperature? High temperature, unit behaves randomly. Low temperatures like a half-field network. So simulated annealing. The process is gradually cools the system from a high temperature to avoid local minima, similar to the annealing process in materials to achieve stable structure. So here benefits is avoid local minima. The randomness introduced by the temperature helps to prevent the network from getting trapped into the local minima. Next, these are the applications: associative memory, constraint satisfaction, and optimization and pattern classification. So associative memory, it remember the patterns and recognize the closest one. Constraint satisfaction problems. So without what is the output, it doesn't matter. It follows the some constraint. If it is satisfied, then only it will solve that problems. Optimization and pattern classification. Based upon the patterns, it will be classified. So these are the applications: associative memory, constraint satisfaction, and optimization and pattern classification. So in this session, we have learned what is the recurrent networks, recurrent neural networks, and we have seen the architecture also. Next, we have seen half-field networks, and we have seen example also. We have seen the formula, how it will be active and deactivate, the weights, x into x transpose. Okay, next we have seen Boltzmann machines and applications. Thank you.